Hi everyone. Now we're going to solve some logarithmic equations. We're finishing up 3, 4, 3, 5. Okay, so in case 1, we're going to deal with equations with one log expression. Something like this. 3 ln of x equals 12. One log expression here. And the first step here is to isolate this basic log expression. We do that by dividing both sides by 3. And we get ln of x equals 4. And then there are a couple of ways that we can go about solving this. First of all, the mathematician's approach. Basically, we're asking, what inverse function can we use to unravel this and get at the x? Well, what's the inverse of the natural log function? It's the base e exponentiation function. Basically, we're going to kick in e's. If m equals n, then e to the m equals e to the n. So we have e, I'll raise this up. We have e to the ln of x equals e to the fourth. Now e to the ln of x, by the inverse properties, we get x equals e to the fourth. Now e to the fourth is a number. It's our tentative solution. It does turn out to be the sole solution, but technically we should check it. Because the thing is, remember that we can only take logs of positive numbers. So we need to check to make sure, well, when we plug in e to the fourth into the original equation, okay, does it all check out? Now, if we're only taking logs of positive values in the original equation, that's a very, very good sign that we're going to be okay. If you plug in e to the fourth, we're only taking the natural log of a positive value, so we should be okay. Although it is good to check completely. In fact, we can go ahead and do the check. All right, so we could do a complete check. 3 times ln of e to the fourth equals 12. Does it equal 12? Well, 3 times ln of e to the fourth is 4. And yes, 3 times 4 is in fact 12. It checks out. Very good. All right. Now, another way to go about doing this is by going to exponential form, meaning we do the zigzag. So remember, ln of x equals 4, all right? Natural log was log base what? Remember, this was often helpful for showing work. ln can be rewritten as log base e. So ln of x equals 4 can be rewritten as log base e of x equals 4. Okay. Now, we can do the zigzag. Rewrite this in exponential form. E to the fourth equals x. The zigzag. E to the fourth equals x. We're basically writing this in exponential form. X equals e to the fourth. Once again, we should check to make sure that when we plug in e to the fourth into the original expression, right? More than anything else, we have to make sure that we're only taking logs of positive numbers. Okay, we should check it formally, and we already have over here. Okay, so we check our tentative solutions to make sure that they check out. Solution set consists of the sole solution e to the fourth. Again, you could have more than one solution or no solutions, maybe all real numbers, but here we just have one solution. Okay, next up. Let's do this example. Solve log of the fourth power of x minus 1, it's good for me to put brackets here, equals -8. And we're going to assume that x has to be greater than 1. It turns out to help us, as we'll see. All right. I don't feel like taking the fourth power of x minus 1. And guess what? You don't have to, because we have the log properties. What can we do with this 4? It's an exponent on x minus 1. We can smack it down by the power rule. 4 times log of x minus 1 equals negative 8. Now here's where this condition, this assumption, helps us out. Okay, because we know that, I'll go here, we know that we're dealing with x minus 1 here, right? We're dealing with x minus 1. So let's take a look here. If we know that x is greater than 1, we can subtract 1 from both sides, and we get x minus 1 is greater than 0. X minus 1 is greater than 0. If x is greater than 1, we know that x minus 1 is greater than 0. So that means that when we do our smackdown, because we know that x minus 1 has to be positive in value, that means we do not need absolute value. See, if we did not have that guarantee, then we would need absolute value. And I'll show you what would happen later on. But since we know that this is positive, under this assumption, we can smack down the 4. We don't need absolute value. All right, so here's our basic log expression now. It's fairly basic. To isolate it, what do? We isolate both sides by the 4. Oh, and by the way, it's assumed to be a common log. That's log base what? Log base 10. Remember, if you're working on a particular problem and you see a log expression like this, you assume it's base 10. So we get log base 10 of x minus 1 equals negative 2. Remember, we divided both sides by 4, and here I decided to clearly indicate that the base is 10. It's assumed to be 10. It was assumed to be 10 way back here. Common log. Okay, now, this is in log form. Let's put this in exponential form. That's when we do the zigzag. 10 to the negative 2 is x minus 1, the zigzag. Converting to exponential form. X minus 1, 10 to the negative 2 is x minus 1, and then I turn them around. Right? 10 to the negative 2 equals x minus 1. Okay, and I'm just turning it around. 10 to the negative 2, as a decimal, let's say, is 0.01. It's a penny. 10 to the negative 2 is 1 over 10 squared, okay, which we know is 1/100th, or 0.01. Okay, the decimal turns out to be easier to manage here. Okay, add 1 to both sides, and we get x equals 1.01. This does turn out to check out. If you plug this into the original, okay, plug in 1.01 here, all of this stays positive. Okay, given the 4th power, that wasn't hard to do. All right, this checks out. It's our sole solution. Our solution set is so.